Hi everyone, this is Safo and welcome back. In the previous episode, we reviewed the MATLAB tools that we will use throughout this series. Today we are going one step further. Instead of only discussing MATLAB command, we will build our first motion simulation for an autonomous underwater vehicle. The model is intentionally simple, but it introduced the fundamental idea behind vehicle dynamic simulation. We will model a vehicle moving in one dimension, compute its velocity and position over time, and visualize the result. To model the vehicle motion, we'll start with Newton's second law. The thrust force accelerates the vehicle forward. At the same time, hydrodynamic drag resists the motion. The balance between these forces determines the acceleration of the vehicle. Our goal is simple. We want to calculate how velocity changes over time. Then we use velocity compute position. Finally, we visualize both quantities using MATLAB. Okay, here as always we begin by clearing the command window, removing variables from memory and closing existing figure. Here we define the physical parameters of our vehicle. M is the vehicle mass, B represents a hydrodynamic drag, and T is the thrust force generated by propulsion system. This parameter determines how the vehicle responds to the external forces. Next, we define the simulation time. The variable dt is the time step used for numerical integration. We simulate the vehicle motion for 30 seconds. You can see here, okay? Before starting the simulation, we allocate memory for position and velocity. Both vectors initially contain 0. Okay, MATLAB performance is generally better when memory is allocated in advance. Okay, and next here we enter the core of the simulation. The for loop allows us to update the vehicle state step by step. At each time step, we calculate acceleration, velocity, and position. Okay, this line implements the dynamic equation. The thrust force pushes the vehicle forward. The drag force opposes the motion. Dividing the net force by mass gives acceleration. Using the acceleration, we update the velocity. This is a simple Euler integration step. The new velocity equals the previous velocity plus acceleration multiplied by the time step. Once velocity is known, position can be updated. Again, we use Euler integration. The new position depends on the previous position and the current velocity. The loop repeats this process for every simulation step until the final time is reached. And here, finally, we visualize the result. The first first subplot shows position, and the second subplot shows velocity. Okay, at this point we have translated a physical motion equation into executable MATLAB code. Let's run the simulation and observe the vehicle behavior. Okay, run. The velocity here starts at 0 because the vehicle is initially at rest. As the thrust force accelerates, the vehicle velocity increases. Over time, drag becomes larger and larger. Eventually, thrust and drag balance each other. At the point the velocity approaches a constant steady state value, and the position continuously increases because the vehicle keeps moving forward. Initially, the curve is non-linear because the velocity is changing. Later, the position becomes almost linear because the velocity approaches a constant value. Today, we built our first complete motion simulation for an autonomous underwater vehicle. Starting from a simple physical equation, we compute acceleration, velocity, and position using numerical methods. This is the foundation of dynamic simulation and control design. In the future episode, we will extend this idea to more realistic AUV models with inertial state and dynamics. Thanks for watching, and I'll see you in the next episode.